Now, the way we're going to do this is we're going to look at partials. So check this out. I'm going to pick some really strategic partials here. All right, S of 1 is 1. S of 2 is 1 plus 1/2, which is 3/2, right? Now, and we're going to watch what happens here, because remember, the reason I'm allowed to do what I'm about to do, and the reason that we've been allowed to do what we've done, particularly with the geometrics, is because we go to infinity, which gives us a lot of leeway. We're not trapped into a finite series. If we were trapped into a finite series, ladies and gentlemen, it would always converge as long as it was defined for all the values. Think about that. If it's a finite series, you always converge because you're adding up a finite number of things. Right, now, I'm going to pick S sub 4. And you may say, well, wait, Ripley, why'd you do that? Well, just watch. S sub 4 is 1 plus 1/2 plus 1/3 plus 1/4. Now, do you agree that this is greater than 1 plus 1/2 plus, now let's look real close, 1/4 plus 1/4, right? And this is equal to 2. So what we're doing is we're growing. I started it at 1, and I went to 3/2, and then I went to 2. Now, why am I allowed to do this? Well, I didn't go to 2. I went to a number greater than 2. I'm getting even bigger. I'm going to grab S sub 8. I'm going to need a little more room here. Now, why did I grab S sub 8? Well, you'll see here in just a sec. It's not coincidence. I'm going to go 1 plus 1/2 plus 1/3 plus, I'm going to do this one all the way out. It's going to drive some of you nuts, but that's okay. Plus 1/6 plus 1/7, that's plus 1/8. If you think about it, this is greater than 1 plus 1/2 plus 1/4 plus 1/4. That's where we got, that's these guys right here. Plus, now think about that. I know that this is going to be 1/8 plus 1/8 plus 1/8 plus 1/8. Correct? Now look at what I'm doing. I know that this sum is going to gather an extra, is going to be greater than an extra 1/2 that's created by these 4 1/8, which means that I'm headed for 2.5 or 5/2. So look at what happened there. When I went from 2 to 4, I picked up greater than a half. When I went from 4 to 8, I picked up another value that was greater than a half. So now instead of going from 2 to, say, a number that's just a little smaller, well, I'm picking up a half. Now, I'm not going to do this whole thing out, but think about what would happen with S16. Well, I know that this is going to be S sub 8 plus, now there's going to be 8 of these terms, so be patient. This is going to be 1/9 plus 1/10 plus 1/11 plus 1/12 plus 1/13 plus 1, it goes for a while, sorry guys, plus 1/15 plus 1/16 plus 1/17 plus 1/18. Or wait, I went way too far, didn't I? Duh. S sub 16. Sorry. Duh. Now, look at this. We know that this value is greater than 1/16 plus 1/16 plus dot 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 plus 1/16, 1, 2, 3, 4, 5, 6, 7, 8 times, right? Plus, of course, whoops, S sub 8, which guess what it's going to spit out? It's going to spit out a 3. So this term is going to be greater than 3. What do you think is going to happen for S sub 32? S sub 32, by the same exact process, is going to be greater than 3.5, 7/2. S sub 64 is going to be greater than 4. S sub 128 is going to be greater than 4.5 or 9/2. You see what's happening? Because I'm allowed to go to infinity, I'm just going to, if I go far enough out, I'm just going to keep adding a half, which means that the thing behaves like something where I can just add a little bit greater than a half if I'm allowed to go far enough out. Now, what does that say? It tells me that the sum, as n goes from 1 to infinity, of 1 over n diverges. And it proves that if the limit as n goes to infinity of a sub n equals 0, it does not necessarily imply that the series a sub n converges. It doesn't imply that. So let's do a quick recap. Let's talk about we have a convergence theorem. This is our first convergence theorem. Actually, it's our second. Let's talk about convergence versus divergence. And you really want to keep track of these. These are really, really important things to sort of write down, and you are going to have to memorize them. They got to be on the hard drive. All right, let's talk about convergence. Convergence versus divergence. Okay? All right, first things first. 1, because I'm going to start throwing all kinds of crazy series at you. If I have this series, let's go as n goes from 0 to infinity. What kind is this? Well, it's geometric. It's our very first good buddy, geometric, and it's a good buddy because we know that it might converge. All right? If absolute R is less than 1, then this implies that S equals A over 1 minus R, and it's convergence. Else, it diverges. All right? Number 2, if the sum, as n goes from 1 to infinity, 0 to infinity, 17 to infinity, who cares, of A sub n. Now you may say, wait a sec, what happened to this? Well, this was a geometric. This guy right here was a geometric series. I'm talking about any series in general. All right? The sum then goes from 1 to infinity of A sub n. If it converges, then this implies that the limit as n goes to infinity of A sub n must equal 0. However, we have this wonderful quick little test for divergence. If the limit as n goes to infinity of A sub n equals infinity plus or minus infinity, or doesn't, wait, sorry you guys, let me back up. I apologize. Does not equal 0, I'm getting crazy, does not equal 0, or doesn't exist, then this implies that the sum as n goes from 1 to infinity of A sub n must diverge. You now officially have 2 rules for convergence or divergence of an infinite series. Okay? Those are going to become really important, and you're going to have to keep them on there. Okay? All right, I'm going to do one more fun little series that's crazy. It's called a telescoping series, which is pretty fun. And then, actually, what I'll probably do is let's talk about the rules of sums, because they're so obvious as to almost be painful. And then I'll show you this cool little convergence series that's pretty awesome. And then we'll be done. All right, thanks for your time and attention. Give me another 5-6 minutes or so. Okay, first things first. These are the rules of sums. Now this is nice because very much like rules about integration or differentiation, we can bust difficult sums up into their sort of from an aggregate to we can de-aggregate our sums. So let's check this out. What do you think? If somebody made you guess, put a gun to your head in the park and made you guess what the sum of A sub n plus B sub n is. And since it's saying, remember, there's no difference between adding and subtracting, we just add negatives, right? What do you think it is? Well, the sum of a sum, strangely enough, is the sum of the sums. So plus minus sum as n goes from 1 to infinity of B sub n. That's a nice little rule there because we get to bust stuff up. And then the other one that's pretty cool is as n goes from 1 to infinity of C, any constant, now that's got to be a constant, times A sub n is equal to, you can probably guess based on what you know about integrals and derivatives and all that stuff, this is the constant times the sum as n goes from 1 to infinity of A sub n. Those are my rules of sum, and they'll be really helpful. All right? That's going to allow us to play with some ugly stuff. We can split them up, just like we did with integrals back in the day. Excuse me. Okay, let's have a little fun. We're going to do this guy. All right, 1 over n times n plus 1. All right, and this is the limit as n goes from 1 to infinity. Now, you ready? This is the thought process that I want you to start going through. Step number 1, always, home base is geometric. Is it geometric? Right? Oh, wait, you know what? I lied. Before I start asking myself if it's geometric or not, home base, let's do a star, because this is before we start having a conversation. Does the limit as n goes to infinity of 1 over n times n plus 1 equal 0? If the answer to that is yes, go on. If the answer to that is no, stop. You have diverged. Well, clearly, 1 over n times n plus 1 goes to 0 as n goes to infinity. Sweet. Is it geometric? I don't know. I'm new to these, Ripley. Why are you asking me crazy questions? Well, let's list some terms. All right, what's the first term? When n equals 1, do you agree I get 1 over 1 times 2, which is a half? When n equals 2, I get 1 over 2 times 3, which is a sixth. Ooh. So to get from here to here, I multiply by a third. If n is 3, I get 1 over 3 times 4. That's a twelfth. I didn't multiply. Crap. Okay, so it's not geometric. Nope. Is it harmonic? Remember, harmonic's free of charge. We know that harmonic diverges. Is it harmonic? Well, clearly, no. So what I'm going to do is I'm going to employ a trick. And some of you, I believe some of my students will refer to me after this trick as a rascal. As soon as I see something like this, excuse me, because I've dealt with these before, I'm not afraid of them. If I see something factored in a denominator, now I don't always want to do this, but just this little niggling feeling in the back of my head says, this might be partial fractions. Let's think about this. If I do 1 over n, or if I do some quantity, a over n plus b over n plus 1, if I had to, I could do it longhand. Let's do it longhand, just for giggles, because we probably haven't done this in a while, right? How do these work again? Excuse me, I get 1 over n times n plus 1 is equal to a n plus a plus bn all over n times n plus 1. Remember this? Just find a common denominator and then you do this. Now I get to ignore my common denominator. And I look at this and I know that a plus b equals 0 because I think of 1 as being 0n plus 1. Remember that? So I know that a plus b equals 0. And I know that a, which is the constant term, has to equal 1. Sweet. So a equals 1, which implies that b equals negative 1. Well, how fun's that? So I know that I can rewrite the sum as n goes from 1 to infinity as 1 over n minus 1 over n minus 1. Now, according to these laws, I can deal with these separately if I want. But the problem is I see that as sort of a divergent and all that good. Oh, wait, and not n minus 1, you ding dong, n plus 1. Otherwise, it wouldn't work. That would get confusing if I busted it up. Remember, if I've taught you anything, it's that even though you have a rule, it doesn't necessarily mean that you have to use the rule. Now, watch what happens. You guys are going to like this. What I'm going to do is I'm going to relist terms, very much like what I did here. My first term, hopefully you agree, is going to be 1 minus 1/2. Correct? Right? Gives me a half, which is right there. My next term is going to be, when n equals 2, it's going to be 1/2 minus 1/3, affectionately known as the sixth. Right? My next term, this guy right here, is when n equals 1. It's going to be when n equals 2. When n equals 3, what do I get? I get plus 1/3 minus 1/4. What's my next term going to be? When n equals, this is n equals 3. When n equals 4, I'm going to get plus 1/4 minus 1/5. Now remember, we're going to infinity. We're going all the way out to infinity. What do you notice is happening? Goodbye, 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 forever. So when I do this, forever, there is no term which will not be canceled out by the subsequent term. So guess what? This converges to 1. Yay! Isn't that a crazy one? That's a fun one. This is called a telescope. I got to change. Let me change color so you can see this sucker. I don't want to use that red anymore. It makes my eyes hurt. This is called a telescoping series. Think about what a telescope, like the old school, like the field glasses or the field pieces. You know what I'm talking about? They were shaped like this, and they had a lens at the end, and the dude's eye was right here, or the gal's, sorry ladies. And this thing would telescope back on it, like an accordion telescopes. A telescoping series. They're funny, they're goofy, and you'll see them again. All right? This is called a telescoping series. You guys, thank you for your time and attention. I know that these are long lectures out of these sections. Just stay on them. Write down the stuff that I tell you to write down and memorize the stuff that I tell you to memorize, because series really are tricky, and we're right at the tip of the spear as far as getting in on these series right now. Bring your questions to class. I look forward to talking to you and playing with series. They're actually really fun, but you do have to stay on top of them. All right? Thanks for your time and attention. Have a great day.